This is a video for OCR Pure Core Mathematics. Second order differential equations 3, modelling with second order differential equations. 3.2, damped oscillations. In a previous video we looked at modelling simple harmonic motion, and we ended up with this differential equation, which has the acceleration proportional to the displacement from the centre and directed back towards it. Its general solution has a constant amplitude and therefore gives us a periodic motion which goes on forever, as you can see on this graph. While this is a good model for some situations, there are many others where the amplitude of the oscillations decreases with time. Think of a pendulum slowly swinging and gradually the oscillations will dampen down, or indeed a mass hanging on the end of a spring. Eventually the amplitude of the oscillations will decrease over time. Those types of oscillations are called damped oscillations. So if we have a look at this differential equation that represents a damped oscillation, this extra term in the middle here comes about as the result of some kind of resistance to the motion related to the velocity, and that explains why it slows down over time. In order to solve this differential equation, we start out with our auxiliary equation, as before. So our auxiliary equation is going to give me lambda squared plus 2 lambda plus 10 is equal to 0. And completing the square, I'm going to get lambda plus 1 all squared plus 9 is equal to 0. And so that gives me that lambda is equal to minus 1 plus or minus 3i. Now the general solution to this then is just going to be x is equal to e to the minus t times some cos 3t's and some sin 3t's. Now if you've seen the previous video on SHM, you might be tempted to replace this with an a sine omega t plus epsilon type thing, but in fact sorting out the constants is much easier whilst it's in this form. There's that written up so you can follow it. So my auxiliary equation and its solutions giving rise to this general solution here. So if we want to find the particular solution for this, for these initial conditions, t equals 0, same thing being applied to both of these, so these are initial conditions, when I've got this general solution. So let's start out with x equals 0 when t equals 0. So that's going to give me 0 is equal to 1 times p, and the q is 0, so that's going to give that p equals 0. So this general solution immediately becomes x is equal to q e to the minus t sine 3t. And now I can look at dx by dt, and that's going to be minus q e to the minus t sine 3t plus 3q e to the minus t cos 3t. And I know that dx by dt is equal to 1 when t equals 0. And if I plug that into there, this bit's going to be 0, and this bit here is just going to be 1, and this bit is going to be 1. So I just get 1 is equal to 3q, and that gives me q is equal to 1/3. And so my particular solution is going to be x equals 1/3 e to the minus t sine 3t. Again, that's written up more neatly. Here's where I've used x equals 0 and t equals 0 gives me that p is 0, so I haven't got any causes in the final solution, so I just get this. Differentiating that and plugging in these initial conditions, I end up with q as a third, and therefore this for the particular solution. If we have a look at the solution curve for this, a couple of things to point out on here. Firstly, notice that this blue dotted line here and here form an envelope for the oscillating function. So over time the amplitude is restricted to between these two blue curves, and these blue curves come from the 1/3 e to the minus t bit of this. And the second thing to notice is that we've got a sine 3t, and that means that the period of the oscillation is going to be 2 pi over 3. In other words, we would expect 3 complete oscillations over 2 pi, or 1.5 oscillations over pi, and if we look at this curve, it does 1 complete oscillation to there and then another half an oscillation to here, so it does in fact have a period of 2 pi by 3. Now this kind of oscillation looks quite realistic in terms of a damped harmonic oscillation, and we will look at the interpretation of this result in more detail in a later video. The next video in this sequence is 3.3, Damped Oscillations, Plotting and Interpreting Solutions.